Right now, there are 6, maybe 7 tropical storms spinning across the Pacific Ocean at the same time, and in the Atlantic there is not a single one. Same planet, same warm water, same week in the middle of hurricane season, one ocean cannot stop making storms and the other cannot start. That is not a coincidence, and it is not luck. It is a single force reaching across the entire planet, flooding one basin with cyclones and slamming the other one shut. And here is the part almost nobody is saying out loud. The quiet ocean, the calm one, the one everybody is relieved about, might be the more dangerous of the two, because the same thing keeping it silent is quietly loading it, like a spring being wound tighter every week. If you want to understand the pattern behind this, and why a dead quiet Atlantic in a year like this is not the good news it looks like, subscribe to the Skylab, because this story is still developing and we are following it every single day. Drop a comment and tell me where you are watching from, and whether the weather where you live has felt strange this month. Now, let us get into it. Part 1. 2 oceans, 1 planet, and a split that should not be possible. Right now, as you watch this, one ocean on this planet is spinning up storms faster than forecasters can name them, and the ocean right next door cannot produce a single one. In the Pacific, there are 6, maybe 7, named tropical systems turning at the same time. Typhoons, tropical storms, depressions, and a fresh disturbance that has already been flagged with an 80% chance of becoming the next one. It is a wall of spinning weather stretched from the waters off China and Japan all the way across to the Central and Eastern Pacific. And then you look at the Atlantic, the ocean that has terrorized the United States for generations, the ocean that gave us Katrina and Sandy and Ian, and it is doing nothing. 3 named storms the entire season. 1 lonely smudge of clouds that forecasters think might, maybe, become a tropical storm in the next day or so. As one meteorologist put it, over the next week the Atlantic looks dead as a doornail. 2 oceans, on the same planet, at the same moment, behaving like they belong to different worlds. And here is the thing I need you to sit with before we go any further, because it is the whole reason this video exists. That silence in the Atlantic is not luck. It is not a break. It is not the ocean taking a season off. It is a symptom. The same invisible force that is flooding the Pacific with storm after storm after storm is the exact force reaching across the equator and holding the Atlantic shut. 1 driver, 2 opposite outcomes, and the terrifying part, the part almost nobody is saying out loud, is that the quiet ocean may be the more dangerous of the 2. Let me give you the answer up front, because I do not believe in making you wait an hour for the point. The force doing all of this has a name. It is called El Nino. You've heard the words before, probably in the context of a rainy winter or a warm Christmas. But what is happening in the Pacific right now is not the mild background version you half remember. This is a strengthening event, an event that forecasters are already describing with a word they do not use lightly: super, a super El Nino. And it is reorganizing the atmosphere of the entire planet, tilting the odds in one basin toward chaos and in the other toward an eerie, loaded calm. That is the promise of everything that follows. By the time we are done, you will understand exactly why the Pacific cannot stop and the Atlantic cannot start. You will understand the single mechanical switch that decides which ocean gets to make storms, and you will understand why a quiet hurricane season in the Atlantic during a super El Nino year is not the good news it looks like. It might be the setup for one storm that overperforms everything. It helps to understand what the word super is actually doing here, because it is not marketing. El Nino is not a storm or an event you can point to on a map. It is a shift in the temperature of a specific band of the Pacific Ocean along the equator, and forecasters measure it with an index, a single number that tells you how far above normal that water has climbed. In an ordinary El Nino, that number sits somewhere around 1 degree Celsius above average, which is roughly 2 degrees Fahrenheit. A strong event pushes toward 1.5. Right now, the most recent weekly reading of that index came in at 2.7 degrees Celsius above normal. That is not a strong El Nino. That is an event flirting with the record books, and the forecast models are pointing even higher, toward 3 degrees and beyond. The last time the Pacific ran this hot along the equator, back in 2015 and into 2016, It produced a hurricane season people still talk about, and a winter that rewrote expectations across the country. That is the scale of the thing sitting in the Pacific right now, and it is still strengthening. When a patch of ocean that large gets that warm, it does not just make its own weather, it bullies the atmosphere of the entire planet. Warm water throws more heat and moisture into the sky above it, and that rising air has to come down somewhere else, which changes wind patterns thousands of miles away. The jet streams shift. The high-altitude winds over distant oceans speed up or slow down. Rainfall patterns that feed continents get dragged out of place. This is why a temperature anomaly in the middle of the Pacific can decide whether the Atlantic makes hurricanes, whether the American Southwest bakes, and whether the coming winter turns stormy in the south. One warm patch of water, pulling strings on a planetary scale, and every symptom we're about to walk through traces back to it. So let us start with what we can actually see, because the raw picture is staggering on its own. Picture a satellite view of the Pacific, that enormous stretch of blue that covers a third of the planet. Normally, even in an active stretch, you might see one organized system, maybe two. Right now you can count them like streetlights. There is a typhoon named Saudal, which climbed to Category 2 strength with sustained winds around 100 miles an hour and gusts pushing past 120, and which tracked right across the Ryukyu Islands, the chain that includes Okinawa. The United States military moved ships and aircraft out of the way ahead of it. That is not a drill anyone runs for a storm that is not real. Behind Saudal there is a tropical storm called Lala. There is another called Isel. There is one named Julio, and one named Nara that is fading now. There are tropical depressions with designations most people will never learn, systems the forecasters simply number, and there is that 80% zone, the next storm loading in the chamber. Count them honestly and you land somewhere between 6 and 7 organized tropical systems in one ocean at one time. There are long-time tropical meteorologists who will tell you they can go years without seeing a basin this crowded. And while all of that spins, the Atlantic sits there with sea surface temperatures that are plenty warm enough for hurricanes. Water that in most years would already have produced several, and it produces almost nothing. That contradiction is not a coincidence you can shrug off. Two things this opposite happening at the same time are almost always being driven by the same underlying cause. And they are. Think about what it actually takes to make a hurricane, because it will make the rest of this make sense. You need warm ocean water to supply the heat and moisture. You need a moist atmosphere so the storm does not choke on dry air. And crucially, you need calm winds up high, winds that do not change much in speed or direction as you climb through the atmosphere. That last ingredient is the quiet one nobody talks about, and it is about to become the most important character in this entire story. Because a super El Nino does something very specific with those winds. In the Pacific, it lays them down flat and lets storms build. In the Atlantic, it cranks them up and rips storms apart before they're even born. That is the split. That is why one ocean is a nursery and the other is a graveyard. And once you see the mechanism, you cannot unsee it, because it explains not just the storms, but the heat baking the southern United States, the strange floods showing up in places they do not belong, and the winter that is quietly being assembled for the months ahead. It all runs back to the same source. So let us go stand in the middle of that overcrowded Pacific first, and look at the storms this pattern cannot stop making, because one of them is doing something you almost never get to watch happen in real time. Part 2. The storms the Pacific cannot stop making. Typhoon. Saudal is the heavyweight in the room, so start there. It reached Category 2 intensity, which on the scale we use for hurricanes and typhoons means sustained winds in the range of 100 to 110 miles an hour, with gusts that were being clocked between roughly 112 and 125 miles an hour. Those are numbers that peel roofs and snap power poles. Saudal drove toward the Ryukyu Islands, the long arc of Japanese islands that includes Okinawa, and as it approached, the United States military did something that tells you everything about how seriously this storm was taken. They moved ships out to sea and flew aircraft away from the path, because a warship tied to a pier in a Category 2 typhoon is a warship you might lose. When the Navy sorties its fleet to escape a storm, the storm is not a forecast on a screen anymore. It is a physical threat to steel and men. But Saudal is only the loudest voice in a very crowded room. Around it, at the same time, are tropical storms with their own names and their own spin. Lala, Isel, Julio, Nara, which is weakening as we speak. Each of these is a self-contained engine, a rotating column of thunderstorms drawing heat out of the ocean and throwing it into the sky. And below them, in the forecaster's language, are the tropical depressions, the systems that have organised enough to rotate but have not yet crossed the wind threshold to earn a name. There is one moving south, there is another moving north, and then there is the 80% zone, the disturbance that models and forecasters agree is very likely to become the next named storm, possibly a typhoon forming over near China. Add the whole inventory together, and you understand why someone counting on screen ran out of fingers and just said, literally, 1, 2, 3, 4, 5, 6, 7 different ones. Now, here is where it stops being a list and starts being genuinely strange. 2 of those systems in the Western Pacific, one drifting north and one drifting south, are set to do something that has an actual name in meteorology. A name most people have never heard. They are going to start orbiting each other. 2 separate low-pressure centres, close enough now that their circulations are beginning to feel one another, will pivot around a shared point in the ocean between them, like 2 ice skaters clasping hands and spinning. This is called the Fujiwara effect, and I want to slow down on it, because it is the kind of thing that looks unnatural the first time you see it on a loop, and understanding it early will save you from a lot of nonsense later. The effect is named after a Japanese scientist named Sakuhei Fujiwara, who described it back in 1921, more than a century ago. What he worked out is that when 2 cyclonic vortices, 2 spinning storms, drift within roughly 1,400 kilometres of each other, which is about 870 miles, they stop behaving as independent objects. They begin to rotate around a common centre of mass, and depending on their relative sizes, one may swing the other around, or they may merge outright into a single larger system. That is the dance forecasters are watching set up right now, and in this case, luckily the 2 storms doing it are out over open water, not forecast to threaten land. But the fact that the Pacific is crowded enough for 2 storms to even find each other and lock into orbit tells you how loaded this basin is. You do not get a Fujiwara interaction in an empty ocean, you need traffic. And the Pacific right now is bumper to bumper. There is a second Fujiwara-style interaction possible over in the Eastern Pacific as well, systems dancing around one another on the far side of the ocean, while the Western Pacific runs its own show. 2 separate corners of the same basin, both busy enough to stage the same rare interaction at the same time. Step back, and the picture is almost absurd. If you did not know better, if you only looked at the Pacific and nothing else, you would assume the whole planet had tipped into some hyperactive storm regime, that hurricanes and typhoons must be exploding everywhere. And that is exactly the trap, because the moment you pan the camera east, across Mexico, across Central America, out over the Atlantic, the entire show goes dark. The same planet, the same season, the same warm late summer water, and nothing. That contrast is the central thread of everything we're doing today, and the Pacific side of it is now clear. This ocean is doing what a super El Nino tells it to do. It is warm where it needs to be warm, calm up high where storms need calm, and moist all the way through. It is, in the language of a meteorologist, an incubator. Every ingredient a tropical cyclone could ask for is sitting on the table, and the atmosphere is handing them out to anything that so much as thinks about spinning. It is worth understanding why the Pacific specifically is the ocean getting all of this, because it is not random favoritism. Start with the water itself. A tropical cyclone is, at its core, a heat engine. It runs on the temperature difference between the warm ocean surface and the cold upper atmosphere, and the warmer that surface water is, the more powerful the engine can become. The Western Pacific holds the largest reservoir of warm water on the planet, a region oceanographers call the warm pool, and during a strong El Nino that warmth spreads and deepens eastward across the basin. What matters is not only the temperature at the very surface, but how deep the warm layer goes. A storm churns the ocean as it spins, dragging up water from below. If the water below is also warm, the storm keeps feeding. If the water below is cold, the storm chokes on its own upwelling. Right now, across much of the Pacific, that warm layer runs deep, which means these storms have an almost bottomless tank to draw from. Then add the second ingredient, the one that decides everything, the winds up high. For a young storm to organise, the winds at the top of the atmosphere and the winds near the surface need to be blowing at roughly the same speed and in roughly the same direction. When they are, the storm can stack itself into a tall vertical column and concentrate its energy. When they differ sharply, when there is strong wind shear, the storm gets tilted and smeared, its heat and moisture blown downwind before a core can form. During this El Nino, the Pacific has been handed calm upper winds and low shear, precisely the condition storms need to build. Warm deep water, low shear, and a moist atmosphere all in the same place at the same time. That is not a coincidence of 6 or 7 separate storms. That is one ocean turned into an assembly line, stamping out cyclones because every station on the line is running. Hold that image, the crowded ocean, the 2 storms circling each other, the 80% zone loading the next one in. Because now we cross the equator and the border, and we go stand in the ocean that has all the same warm water and somehow cannot make a thing, the Atlantic. And the emptiness there is not peace. It is the more unsettling half of this story, and it is where the word terrifying in our title actually earns its place. Part 3. The Ocean That Cannot Start. A single storm. Here is the number that should stop you. 3. 3 named storms in the Atlantic for the entire season so far. In a basin that, in a busy year, can run through a dozen names by this point on the calendar, that is a near-empty tally. And it gets stranger when you look forward instead of back. Forecasters running the models see essentially nothing coming. The main American forecast model, the one meteorologists lean on for the medium range, shows no tropical systems developing across the Atlantic over the following 7 days, a full week, and the ocean is projected to stay shut. The phrase one forecaster reached for was that the Atlantic looks dead as a doornail. There is exactly one candidate on the board, a single disturbance that might organise into a tropical storm within about a day, a storm that would take the name Dolly if it forms. It may come together east of the Lesser Antilles, that arc of islands guarding the eastern Caribbean, or it may fall apart. Nobody knows yet because there is nothing there yet to track. Now, why does that matter so much? Why spend time on an ocean that is not doing anything? Because an empty Atlantic in late August is not normal, and the reason it is empty is the same reason the Pacific is overflowing. This is the payoff of the split. The same super El Nino that laid the upper winds down flat over the Pacific is doing the precise opposite over the Atlantic. It is reaching across the tropics and cranking the high-altitude winds up, flooding the basin with dry, sinking air, and turning the main development region, the stretch of ocean where Atlantic hurricanes are normally born, into a place where storms simply cannot get organised. The water is warm, the fuel is there. But the atmosphere above it is hostile, and no amount of warm water can build a hurricane if the winds up high are tearing the top off of it as fast as it tries to rise. So the Atlantic sits there, warm and quiet, and most people read that quiet as good news. No storms, no landfalls, no evacuations, no boarded up windows on the Gulf Coast. And on the surface, for right now, that is true. But I want you to hold on to a distinction that is going to matter enormously, because it is the hinge this entire video turns on. There is a difference between an ocean that is calm because it is exhausted, and an ocean that is calm because something is holding it down. The Atlantic right now is the second kind. It is not quiet because it has spent its energy. It is quiet because a lid has been pressed onto it from above, and a lid can be lifted. Think about what has actually been happening under that lid all season. Every year, when Atlantic hurricanes form and move across the ocean, they do something useful, in a strange way. They churn the water. A hurricane is a giant mixing machine, dragging cooler water up from below and spreading the surface heat around, spending the ocean's stored energy as it goes. It is the ocean's release valve. But this season, with almost no storms forming, that mixing has not happened. The heat that would normally have been stirred up and bled off by a parade of tropical systems is still sitting there, undisturbed, stacked up in the upper layer of the ocean. The Atlantic has been warming all summer and spending almost none of it. The tank is full and nobody has touched the fuel. That is what makes forecasters uneasy when they look at this pattern, and it is the exact reason the meteorologist whose analysis anchors this story kept circling back to one warning. If even one system manages to get going in the Atlantic, if the shear relaxes for just a few days over that untouched warm water, while a seed disturbance happens to be sitting there, it could intensify explosively. It could skyrocket, in his words, toward a major hurricane and do it fast because there would be nothing to slow it down. No cooler water churned up by earlier storms, no competition, just a full reservoir of heat and a single storm with the whole ocean to itself. The quiet is not the absence of danger, the quiet is the danger being stored. To really feel why forecasters are uneasy, you have to picture where Atlantic hurricanes are supposed to come from this time of year. There is a stretch of ocean that runs from the west coast of Africa across to the Caribbean, a warm corridor that meteorologists call the main development region. Most of the big, long-track Atlantic hurricanes, the ones that become household names, are born there, from clusters of thunderstorms that roll off the African coast and spin up as they cross the open water. In a normal season, by late August, that corridor is a conveyor belt, launching wave after wave. Right now, it is a dead zone. The El Niño-driven winds aloft are tearing across it, and the sinking dry air is smothering the thunderstorm clusters before they can consolidate. Dry air is a hurricane's poison. When a developing storm pulls dry air into its circulation, the moisture that should be condensing and releasing heat instead evaporates, and the whole process stalls. So the waves come off Africa, and they die, one after another, in water that is more than warm enough to sustain them. And that is the cruel twist. The water temperature is not the problem. If you measured the sea surface in that corridor, you would find it plenty hot, in many places running warmer than average, because the ocean has been absorbing heat all summer, with almost no storms to spend it. Scientists have a concept for the ceiling this sets, called potential intensity. It is the theoretical maximum strength a storm could reach given the ocean heat available to it, and in the Atlantic right now that ceiling is high. The only thing keeping storms far below their potential is the shear and the dry air pressing down from above. Take that lid away, even briefly, and the gap between what the storms are doing and what they could do is enormous. That gap is the danger. The same thing happened in the last comparable Super El Niño, when the Atlantic ran unusually quiet even as the water stayed hot. A season that looked calm right up until you remembered how much unused energy was sitting in it. This is the coiled spring, and it is the heart of the terrifying pattern in our title. A Super El Niño gives you a Pacific that cannot stop and an Atlantic that cannot start, and the instinct is to feel relief about the second half of that. But the same force suppressing the Atlantic is loading it. It is compressing the spring tighter with every warm, stormless week. The lid holds right up until it does not, and the lone disturbance that might become Dolly, out there east of the islands, is the first small test of whether the lid is going to hold at all. We will come back to Dolly because that storm, if it forms, is where this abstract danger becomes a specific one with a track and a name. But first we have to open up the machine itself. I have told you that El Niño flattens the winds in one ocean and cranks them up in the other, and you have taken that on faith so far. Now I want to show you exactly how a warming patch of water, thousands of miles away in the Pacific, reaches across an entire planet to decide whether the Atlantic gets to make hurricanes. Because once you understand the switch, the wind shear, you understand everything. You understand the storms, the silence, the heat over America, and the winter still being written. It all runs through one mechanism, so let us go find it. Part 4. The Master Switch. Called wind shear. I have used the phrase wind shear several times now, and I have asked you to trust that it matters. It is time to pay that off, because wind shear is the single mechanical switch that decides which ocean gets to make storms, and once you understand it, the entire split between the Pacific and the Atlantic stops being a mystery and becomes almost obvious. So let us build a hurricane from the ground up and watch exactly where shear kills it. A tropical storm begins as a loose cluster of thunderstorms over warm water. Warm, moist air rises out of the ocean surface, cools as it climbs, and the water vapor in it condenses into cloud and rain. That condensation releases heat, and that released heat is the fuel. It warms the surrounding air, makes it rise faster, which pulls in more moist air from below, which rises and condenses and releases more heat. It is a feedback loop, and if nothing interrupts it, the loop tightens into a spinning, stacked column, a chimney of rising warm air with a low-pressure center at its base that sucks in wind from all directions. That organized column is a tropical cyclone. The critical word there is stacked. The storm has to build itself as a roughly vertical tower, with the circulation at the bottom lined up under the circulation at the top, so that all the released heat piles up in the same place and reinforces the center. Now introduce wind shear. Wind shear simply means the wind changes as you go up. Maybe near the surface the wind is gentle from the east, but 8 or 10 miles up it is roaring from the west at 60 miles an hour. When that happens to a developing storm, the top of the tower gets blown downwind while the bottom stays put. The chimney tilts, and a tilted chimney does not draw. The heat being released up high is now displaced away from the low pressure centre at the surface, so it can no longer reinforce it. The moist air gets sheared off and scattered. The feedback loop breaks before it can tighten. This is how storms die in warm water. Not from lack of fuel, but from being pulled apart faster than they can assemble. Shear is the wind tearing the roof off the engine while it is still trying to start. Here is the part that makes El Nino the villain of this whole story. A super El Nino does not just sit in the Pacific being warm. By warming that equatorial water, it changes where the biggest thunderstorm activity on the planet happens, and that in turn changes the high-altitude wind patterns stretched across the entire tropical belt. Over the Pacific, the pattern that results lays the upper winds down, low shear, calm aloft, exactly what a storm needs to stack itself vertically. Over the Atlantic, the same reorganization does the reverse. It strengthens the upper-level winds screaming across the main development region, cranking the shear up to levels that shred storms on contact. One ocean gets the calm, the other gets the blades, same driver, opposite settings, and the switch that flips between them is wind shear. This is the mechanism at the center of everything. Every strange thing we're looking at today runs through this one idea. The 6 or 7 Pacific storms are what low shear over warm water looks like. The empty Atlantic is what high shear over equally warm water looks like. The forecaster's warning about a single storm skyrocketing in the Atlantic is a warning about what happens if that high shear relaxes for even a few days. And the reason the whole pattern is so lopsided and so stubborn is that the El Nino driving it is not a normal one. It is a super event, strong enough to hold these opposite settings in place across 2 oceans for weeks on end. Picture it happening to one of those African waves in real time, because this is the death that repeats over and over in the Atlantic right now. A cluster of thunderstorms rolls off the coast, well organised, sitting over water near or above 30 degrees Celsius, which is around 86 Fahrenheit, more than warm enough. For a day it looks promising. The thunderstorms deepen, a spin begins to develop near the surface, and then the upper winds get hold of it. The tall thunderstorm towers, which were leaning straight up, start to tilt to the west as the high-altitude flow drags their tops away. The rain and the released heat, which had been stacking neatly over the developing centre, get displaced dozens of miles downwind. The surface spin, now cut off from the heat engine that was supposed to feed it, weakens and unwinds. Within another day the whole system is a disorganised sprawl of clouds with no centre at all. Multiply that by wave after wave all season, and you have the empty Atlantic we are looking at. It is not that the storms never try. It is that they are being executed on arrival. Contrast that with what the absence of shear allows, because it is the mirror image, and it explains the Pacific perfectly. When the upper winds are calm, those same thunderstorm towers rise straight and true. The heat stacks exactly over the centre. The surface pressure falls, the winds pull in harder, an eye can form, and the storm tightens into the compact, powerful engine that becomes a typhoon. Nothing is tearing the roof off. The engine gets to run at full throttle. That is why Sudel could climb to Category 2, and why the basin around it is littered with systems at every stage of development. Same physics, opposite outcome, and the only variable that changed between the 2 oceans is the wind aloft. There is one more thing Shear does that matters for where this story is going. Because it is a wind pattern, and not an ocean temperature, Shear can change fast. Ocean heat takes months to build and months to bleed away, but the upper winds can back off in a matter of days if the atmosphere hiccups, if a pattern shifts, if the thunderstorm activity in the Pacific pulses differently for a week. That is the trapdoor under the Atlantic. The warm water is a slow, patient thing that will still be there in September and October. The shear holding it down is a fast, fickle thing that could step aside at any moment. So the danger is not that the Atlantic stays quiet. The danger is precisely that the one variable keeping it quiet is the one variable that can vanish overnight, over an ocean that has spent all season stockpiling fuel. Keep that asymmetry in mind, because it is the reason a calm map is not a calm situation. Now let us zoom out and watch how a single warm patch of Pacific water manages to reach across the whole planet to throw that switch. Part 5. How one warm patch rules an entire planet. There is a fair question sitting under everything I've told you so far. How does a change in ocean temperature in one specific part of the Pacific reach all the way to the Atlantic, to the American Southwest, to the jet stream over the northern plains? It sounds like too much power for one patch of warm water, but the atmosphere is a connected fluid, and there is a well-understood machinery that carries the influence of El Nino around the globe. Understanding it is what separates knowing that El Nino causes these things from understanding why, and the why is what lets you see what comes next. Start with the normal state of the Pacific, the way it usually sits. In a typical year, trade winds blow from east to west along the equator, pushing warm surface water toward Asia and Australia, and piling it up in the west. That leaves the eastern Pacific off South America relatively cool, because cold water wells up from below to replace what the winds pushed away. Above this setup runs a great loop of air called the Walker Circulation. Air rises over the warm western Pacific, where all the thunderstorms and rain are, travels east at high altitude, sinks over the cool eastern Pacific, and returns west along the surface as those same trade winds. It is a conveyor belt of air laid sideways across the tropical Pacific, and it is one of the fundamental engines of the planet's weather. El Nino breaks that engine. When the trade winds weaken and the eastern and central Pacific warm up, the warm water and the rising air and the thunderstorms all shift eastward, toward the middle of the ocean. The Walker Circulation stalls and reorganizes, and because everything in the atmosphere is connected, that reorganization does not stay local. The shifted zone of a rising air changes where air has to sink elsewhere, and air that is sinking is air that is drying out and suppressing storms. During El Nino, one of the places that ends up under enhanced sinking, drying, hostile air is the Atlantic hurricane corridor. The same shift also alters the high-altitude winds streaming across the tropics, and it is this altered flow that ramps up the wind shear over the Atlantic while calming it over the Pacific. So the chain is: warm water shifts east, thunderstorms shift east, the great atmospheric loop reorganizes, and the downstream effect lands on the Atlantic as sinking air and high shear. That is how a patch of ocean rules a planet, not by magic but by bending a circulation that touches everything. Once you see that chain, the American weather makes sense too, and we will get to it in detail later. The same reorganized flow that suppresses the Atlantic also reshapes the jet stream over North America, and that is why the pattern shows up as heat in one place and unusual storms in another. But hold that thought, because the point right now is simpler and more important. There is one driver here. Not a coincidence of a busy Pacific and a quiet Atlantic and a hot Southwest all happening to occur together. One driver, the Super El Nino, reaching through one machine, the reorganized tropical circulation, to produce every one of these effects at once. When you understand the machine, the effects stop looking like separate news stories and start looking like what they are, which is a single planetary event with many faces. You can actually see the fingerprints of this reorganization in the ocean itself, not just the air. Under normal conditions, because the trade winds pile warm water in the west, the boundary between warm surface water and cold deep water, a layer oceanographers call the thermocline, sits deep in the western Pacific and shallow in the east. During a strong El Nino, as the trade winds collapse, that tilt relaxes. Warm water sloshes back eastward, the thermocline in the central and eastern Pacific deepens, and the cold upwelling off South America that normally keeps that region cool gets shut off. This is why the index we track keeps climbing. It is measuring the surface expression of an entire ocean rearranging its heat, and every bit of that rearrangement feeds back into the air above it, reinforcing the eastward shift of the thunderstorms and locking the reorganized circulation in place. Ocean and atmosphere are not two separate systems here. They are one coupled machine, each one pushing the other further into the El Nino state. The last 2 times this machine ran at full strength, the world got a preview of what it does. In the winter of 1997 into 1998, and again in 2015 into 2016, the Pacific warmed to comparable extremes, the Walker Circulation reorganized hard, and the consequences showed up on every continent. Droughts in some places, floods in others, coral bleaching across the tropics, and, relevant to us, badly suppressed Atlantic hurricane seasons paired with hyperactive Pacific ones. Those events are the closest analogues we have to what is unfolding now, and they are the reason forecasters can speak with such confidence about where this is heading. They have watched this exact machine run before. The dials are in the same positions, the outputs are lining up the same way. Scientists have a word for these long-distance links between a change in one part of the climate system and weather far away, teleconnections, and El Niño is the most powerful teleconnection engine on the planet. The idea is that the atmosphere behaves like a single connected medium, so a large enough disturbance in one place sends its influence rippling outward to distant regions in consistent, repeatable ways. Warm the equatorial Pacific enough, and the pattern of ridges and troughs it produces downstream is not random. It falls into recognizable arrangements that show up in the same regions event after event. That is why forecasters can say, with a straight face, that a temperature anomaly near the equator tells them something about the coming winter over North America. They are reading a teleconnection that has held across many past events. This is also why the influence does not fade with distance the way you might expect. A warm patch of ocean does not simply warm the air right above it and stop. It changes where the great columns of rising tropical air sit, and because what goes up must come down, it forces compensating sinking motion in specific distant places, which suppresses storms there, and it shifts the jet streams that steer weather across whole continents. The effect can actually be strongest thousands of miles from the source, over the Atlantic, over North America, over regions that have no obvious connection to a patch of the Pacific, until you trace the chain of cause and effect that links them. Distance is not protection from a teleconnection. In some ways, it is the whole point of one, and this is where the strength of the event matters enormously. A weak El Niño nudges the Walker circulation. A super El Niño shoves it, hard, and holds it there. The stronger the warm anomaly in the Pacific, the more decisively the whole loop reorganizes, the more completely the Atlantic gets suppressed, and the more extreme and persistent the downstream weather becomes. That is why forecasters keep coming back to how strong this particular event is. It is not just that El Niño is present, it is that El Niño is present at a magnitude that turns tendencies into near certainties. A weak event might let a stray Atlantic hurricane slip through now and then. A super event slams the door and leans on it. Which brings us to the actual numbers behind this event, because they are the reason everyone from government forecasters to the meteorologist whose analysis anchors this story keeps using that word, super. Let us look at exactly how hot the Pacific has gotten, and why it may not be finished. Part 6. A Super El Niño by the Numbers. We covered a piece of this ocean story just a few days ago, in our video on the record heat building beneath the surface of the Pacific, and if you watch that one, some of this will click into place fast, but you do not need to have seen it, because the numbers stand on their own, and they are worth saying plainly. The way scientists track El Niño is by watching the temperature of a specific rectangle of ocean along the equator in the central Pacific. They compare its temperature to the long-term average and report the difference as an index. That index is the single best gauge of how strong an El Niño is, and it is the number that decides how hard the atmospheric machinery we just walked through gets pushed. The most recent weekly value of that index came in at 2.7 degrees Celsius above average. To put that in the units most of us feel, that is nearly 5 degrees Fahrenheit above normal across an enormous stretch of ocean. That may not sound like much when you're thinking about the air temperature outside your window, but for a body of water that size, holding that much heat, it is colossal. The official classification scales that forecasters use to rank these events top out at 2 degrees. This event has already run past the top of the ordinary scale by more than half a degree, and it is still climbing. The national forecasters have an advisory in effect and put the odds of this becoming a very strong event through the coming fall and winter at greater than 90%. That is about as close to a sure thing as long-range forecasting ever gets. And a number of the computer models pushing the forecast forward take the index to 3 degrees Celsius or higher, which would place this among the strongest El Niño events ever measured. There is one more piece to the picture that makes it even more striking, and it is the thing that connects this to the larger story of a warming planet without me having to editorialize. This super El Niño is not happening on top of a stable, unchanging ocean. It is happening on top of an ocean that has been warming for decades. So the raw temperatures being reached are not just high for an El Niño. They are pushing into record territory even compared to past strong events, because the natural warm swing of El Niño is now riding on an elevated baseline. Both things are true at once. There is a genuine, natural, cyclical warm event, the kind the Pacific has produced for as long as we have records. And it is unfolding in an ocean that starts warmer than it used to, so the peaks land higher. You do not have to pick between the two explanations. The measurements simply show both. Why does the exact number matter so much to a story about storms? Because everything downstream scales with it. A stronger index means a more completely reorganized atmosphere, which means more thoroughly suppressed shear over the Pacific and more thoroughly cranked shear over the Atlantic. It means the split we are watching is not a marginal, could go either way situation. It is being forced by one of the strongest such events on record, which is exactly why the Pacific is not just active, but overwhelmed, and the Atlantic is not just below average, but nearly shut. The magnitude is the reason the pattern is so lopsided and so durable. And it is the reason the forecast does not expect this to flip back anytime soon, with little sign of the event breaking down before spring of next year. This is not a passing configuration. It is the state of the planet's largest ocean for months to come. It is worth putting this event next to those historic analogues by the numbers, because it tells you where we sit. The strong events of the late 1990s and the mid-2010s peaked with that same index somewhere in the range of 2 1/3 to about 2.5 degrees Celsius above average at their strongest. This event is already reading 2.7 and is forecast to keep climbing toward 3. In other words, we are not looking at something merely comparable to the big ones people remember. We are potentially looking at something that meets or exceeds them, and the year is not even into the peak El Nino season yet, which typically comes in late fall and early winter. The events that gave us the winters people still talk about had not yet reached, at this same point on the calendar, what this one has already reached. That is what forecasters mean when they refuse to call this ordinary. The trajectory is steeper, and the starting point is higher. There is also a quieter reason the exact figure carries weight this year, and it has to do with how these events are now measured. Because the background ocean has warmed, the scientists who track El Nino have had to be careful that they are measuring the true swing of the cycle, and not just the rising baseline underneath it. When they account for that, this event still stands out as exceptionally strong, which means the storm-suppressing, planet-reorganizing power we have been describing is real, and not a statistical artifact of a warmer world. The Pacific genuinely is running one of the most powerful El Nino events in the modern record, by the careful measure and the raw one alike. That is the engine behind the 6 or 7 storms, behind the empty Atlantic, and behind everything still to come. There is a planetary consequence to an event this strong that is worth naming, because it connects the storms to the bigger picture. When the Pacific dumps this much heat into the atmosphere during a strong El Nino, global air temperatures tend to spike, and the biggest El Nino years have repeatedly coincided with the warmest years ever recorded worldwide. The ocean has been storing heat, and a super El Nino is partly the act of the Pacific releasing a surge of it into the sky. That matters for our story in a direct way, because a warmer atmosphere and warmer oceans raise the ceiling on what storms can do everywhere, including the Atlantic. The same event suppressing the Atlantic by count is nudging up the potential intensity of anything that does break through, on top of all the unspent local heat already sitting there. It also explains why forecasters treat this as a whole system event rather than a regional quirk. The index is a single number, but behind it sits a redistribution of heat across the largest ocean on Earth, with consequences that touch global temperature records, tropical rainfall on multiple continents, and the storm behavior of 2 separate basins at once. When an event reaches this magnitude, it stops being a footnote in a seasonal outlook and becomes the dominant story of the planet's year. That is the company this El Nino is keeping, and it is why every downstream effect we are tracking carries the weight it does. But numbers on an index can feel abstract, so let me anchor them to a real consequence, and it is the one this whole video keeps circling. A super El Nino of this magnitude does not just suppress the Atlantic a little, it suppresses it hard, all season, which means the Atlantic's warm water goes almost entirely unspent, which means the reservoir of unused ocean heat we talked about earlier is not a small thing. It is the natural result of the strongest kind of El Nino doing its job thoroughly. The stronger the event, the quieter the Atlantic, and the quieter the Atlantic, the more loaded it becomes. The magnitude that makes the Pacific overflow is the same magnitude that winds the Atlantic's spring the tightest. And that is the paradox we now have to face head-on, because it is the reason a record-breaking, historically strong El Nino producing a dead-quiet Atlantic is not the reassurance it appears to be. It might be the most dangerous version of a quiet season there is. Part 7. Why a quiet Atlantic is not a safe one. We have arrived at the idea this entire video is built around, so I want to slow all the way down and get it exactly right, because it runs against your instincts, and that is precisely why it is dangerous. The instinct is simple and reasonable. No Atlantic storms means no Atlantic threat. An empty map in late August feels like a gift, like the Gulf Coast and the East Coast have been handed a free pass. And in the narrowest sense, for this exact week, that is true. There is nothing bearing down on anyone. But the reasoning that gets you from an empty map to a safe season is broken, and understanding why is the difference between being reassured and being ready. Go back to what has been happening to the Atlantic all summer, under that lid of sheer and dry air. The ocean has been absorbing sunlight and warming, the way it always does through the summer. But normally that accumulating heat gets spent. Tropical storms and hurricanes form, and each one acts as a release valve, converting ocean heat into wind and churning the sea as it goes, dragging cool water up from below and leaving a trail of mixed, cooler ocean behind it. A busy season is, in a strange way, an ocean bleeding off its heat in controlled bursts. This season, with the sheer slamming storm after storm before it can organise, that release has not happened. The heat has gone in and almost none has come out. The Atlantic is not a spent ocean, it is a charged one. Now layer on the concept forecasters use to think about a storm's ceiling, potential intensity. It is the theoretical maximum strength a hurricane could reach given the heat available in the ocean beneath it. The more unspent heat, the higher the ceiling. And in the Atlantic right now, because the heat has been accumulating untouched, that ceiling is high across huge stretches of the basin, including the warm water near the islands and in the Gulf. The only reason storms are running far below their ceiling is the lid, the shear, the dry air. Those are atmospheric conditions, and here is the crucial fact we established earlier. Atmospheric conditions can change in days. Ocean heat changes over months, so you have a high ceiling held down by a low, fast-moving cap over water that will stay hot long after the cap could lift. Put those pieces together and the scenario forecasters quietly worry about writes itself. Suppose, sometime in the weeks ahead, the shear relaxes over a patch of that warm water, even for a few days, and a seed disturbance happens to be sitting there when it does. With no competition, no cooler water churned up by earlier storms, and a nearly bottomless supply of heat, that storm would not just develop, it could intensify explosively, climbing from a disorganized cluster to a major hurricane far faster than the historical average, because every break that normally slows a storm down has been removed. The meteorologist whose analysis anchors this story kept returning to that exact word, skyrocket. One system, if it gets going, could skyrocket, because the ocean is primed and there is nothing in its way. That is rapid intensification, the single most dangerous behaviour a hurricane can exhibit, because it is the hardest to forecast and it gives coastal communities the least time to react. This is the coiled spring in full. The quiet is not the opposite of danger. The quiet is danger being stored, wound tighter with every warm and stormless week. A super El Nino produces a suppressed Atlantic, and a suppressed Atlantic in a warm year is not an empty threat, it is a loaded one. The very strength of the El Nino that is keeping the lid clamped down is the same strength that is loading the most energy underneath it. And the lid is the fickle part. It holds until an atmospheric pattern shifts, and then, over that specific patch of water on that specific week, it might not. That is why forecasters look at a dead quiet Atlantic during a historic El Nino and feel something other than relief. They are not looking at an ocean that cannot make a storm. They are looking at an ocean that has been told to wait. And the thing about waiting is that it ends. It is worth understanding why rapid intensification is the specific nightmare, because it is not just about a storm being strong, it is about time. When a hurricane strengthens slowly, coastal communities get days of escalating warnings, time to order evacuations, time to move people inland, time to board up and get out. When a storm undergoes rapid intensification, especially close to shore, all of that time collapses. A system that was a modest tropical storm one evening can be a major hurricane the next morning, and the people in its path go to bed thinking they will get rain and wake up to a catastrophe already bearing down. It is the hardest thing in the field to forecast, because it depends on small-scale processes inside the storm's core interacting with exactly the ocean and sheer conditions we have been describing. And the single most reliable ingredient for it is deep, warm, unspent ocean heat, which is precisely what the Atlantic has been stockpiling all season. The loaded ocean does not just raise the ceiling on how strong a storm can get, it raises the odds that a storm reaches that ceiling fast, with the least warning, at the worst possible moment, That is the quiet horror underneath a calm map. It is not that a monster is guaranteed. It is that the conditions that make the fastest, least predictable, most dangerous kind of intensification possible are being assembled and held in reserve. Every warm, stormless week deepens the reservoir and tightens the spring. The Atlantic is not resting. It is being prepared. So the question stops being whether the Atlantic is active and becomes something sharper. Is there a seed out there that could be the one? Is there a disturbance that could test whether the lid holds? As it happens, right now, there is exactly one. A single smudge on the map that forecasters think could become the season's next named storm within about a day. Its name, if it forms, would be Dolly. And whether it fizzles or whether it becomes the first real test of everything we just described is, at this moment, genuinely unknown. Let us go look at it. Part 8. Dolly and the first test of the lid. On the Atlantic map right now there is precisely one area worth watching, a single disturbance that forecasters have outlined as having a chance to organise into a tropical storm within roughly the next day. If it does, it takes the next name on the list, Dolly. And I want to be careful and honest about it, because the honest version is more interesting than any hype. We do not know what Dolly is going to do. We do not even know for certain that Dolly will form. That uncertainty is not a weakness in the forecast. It is the whole point, because that single disturbance is the first live test of whether the lid over the Atlantic is going to hold. Here is what makes it worth watching rather than dismissing. The disturbance may try to come together east of the Lesser Antilles, that curving chain of islands that forms the eastern boundary of the Caribbean, the islands like Antigua, Guadeloupe, Dominica, and Martinique that catch the first blows of storms moving in from the open Atlantic. A system organising in that longitude has a long stretch of very warm water ahead of it if it survives, and the deeper into the Caribbean and toward the Gulf it gets, the warmer and the more untouched that water becomes. The main forecast model does not currently develop it, showing that dead doornail Atlantic for the next 7 days, but models struggle with weak, forming systems, and the forecaster's own red leaves the door open in a way the model does not. That gap between the model and the human forecast is exactly where the uncertainty lives. It is worth understanding how forecasters actually watch a system like this take shape, because the next day or two is the window where everything gets decided. It starts with satellite. Forecasters watch the disturbance around the clock from above, looking for the signs that a loose cluster of thunderstorms is starting to organise, a tightening of the spin, a persistent centre, deep convection wrapping around a core rather than sprawling in a shapeless mass. They translate what they see into the odds you have probably noticed on a tropical outlook, the percentage chance of development over the next couple of days and the next week. Those numbers are not guesses pulled from the air. They are a trained read of whether the environment ahead of the system will let it come together or tear it apart. If the disturbance gets close to becoming a tropical storm and could threaten land, the tools escalate. Aircraft can be sent directly into the system to measure its winds and pressure from the inside, data no satellite can fully replace, and that reconnaissance is what usually confirms whether a storm has truly formed and how strong it really is. All of that machinery is on standby for exactly the kind of smudge sitting east of the islands right now. The point is that this is not a situation anyone is ignoring. It is being watched with the full apparatus of modern forecasting, precisely because the ocean beyond it is so primed that no potential seed can be safely dismissed this year. And yet, for all that watching, the honest answer remains that the system has to reveal itself. Forecasters can measure the environment and estimate the odds, but a weak disturbance in a hostile but not impossible setup is genuinely uncertain until it either organises or falls apart. That uncertainty is not a failure of the tools. It is the nature of watching a coin flip in progress, and it is why the outlook speaks in probabilities rather than promises. Think about the two ways this can go, because they map perfectly onto the coiled spring idea. In the first version, the shear and dry air that have smothered every other Atlantic wave this season do the same to this one. Dolly either never forms or spins up briefly and gets torn apart, and the lid holds. The season stays quiet and the reservoir of unspent heat keeps building for whatever comes next. In the second version, this disturbance happens to find a window, a patch, and a moment where the shear backs off, and it gets its feet under it over that warm, charged water. If that happens, the same physics we walk through would apply. It would have room to intensify potentially quickly, with the whole loaded ocean in front of it. Nobody can tell you yet which version you're going to get because the storm that would decide it does not fully exist yet. That is the strange tension of watching a Super El Nino season. Every disturbance that pops up in the Atlantic is a coin flip against the lid, and most of them lose. Wave after wave has already lost this year, which is why the tally sits at 3 named storms, but the ocean underneath keeps getting warmer and more loaded with each loss, so the stakes of any single coin flip that does come up the other way keep rising. Dolly is this week's flip. It will very probably lose, like the others, but it is worth watching precisely because the cost of the one that eventually wins goes up every week. The Atlantic stays quiet. A quiet season is not a series of non-events. It is a series of near misses over an ocean that is being charged the entire time. Geography is part of why this particular disturbance is worth a second look. A system that organises east of the Lesser Antilles sits at the mouth of a funnel. If it survives the islands, the path ahead leads into the Caribbean Sea and potentially toward the Gulf, and those are among the warmest and most storm-favourable waters on the planet in late summer, made even warmer this year by a season with almost no storms to churn them. The farther west such a system travels, the deeper the warm water tends to run, and the more room it has to organise if the shear ever eases. That is the pathway forecasters watch with the most care, not because it is likely on any given disturbance, but because it is the track where a loaded ocean and a surviving storm could meet. The main model keeping the whole basin quiet for a week is reassuring, but models have a known weakness with weak forming systems, and the forecasters leaving the door cracked open are respecting exactly that blind spot. None of this is a forecast that Dolly will become something dangerous. It is a description of why a single, uncertain smudge on an otherwise empty map deserves attention in a year like this one. In a normal season, a disturbance the model does not develop is barely worth a mention. In a Super El Nino season, with the Atlantic loaded the way it is, every disturbance is a test of the lid, and the tests keep coming even when the map looks dead. It is worth remembering too that a name like Dolly is not a measure of danger, only of sequence. The Atlantic uses a preset list of names, assigned in order as storms reach tropical storm strength, so Dolly being near the top of the alphabet simply reflects how few storms have formed this year. In a busy season, the basin would be many names deeper by late August. The near-empty position on the list is itself a symptom of the suppression we have been tracking, a quiet marker of the lid holding. But a low letter on the list says nothing about what any individual storm can become, because the ocean does not care what a system is named. It only responds to heat and shear, and those are set by the pattern, not the alphabet. The islands in the potential path are worth keeping in mind as well, because the Lesser Antilles are home to millions of people spread across small land masses with limited room to retreat from a storm. For those communities, a system organising to their east is not an abstraction. It is the direction every dangerous storm comes from. That is another reason forecasters watch even a low-confidence disturbance in that longitude with care. It is not that this particular one is likely to threaten them. It is that the setup, a seed organising upstream of vulnerable islands over warm water, is exactly the one that demands attention in any year, and demands a little more of it in a year when the water downstream is this loaded. And notice how completely this ties back to the central thread. Dolly is not a separate story from the 6 or 7 storms spinning in the Pacific. It is the same story, seen from the other side of the switch. The Pacific storms are what happens when El Nino hands an ocean-low shear and warm water. Dolly's struggle is what happens when the same El Nino hands the other ocean high shear over water that is just as warm. One driver, 2 oceans, and a single disturbance in the quiet one that could, under the right and unlucky conditions, turn the quiet into the loudest kind of noise. Whether it does or not, the pattern that governs it is the same pattern doing everything else, and to see how reliably that pattern behaves, it helps to look at the last 2 times the planet ran this exact experiment. Because we have watched a Super El Nino load a quiet Atlantic before, and we know how those seasons ended. Part 9. What the last 2. Super El Ninos actually did. We are not flying blind here, and that is what makes the pattern in our title more than a scary phrase. The planet has run this experiment twice in recent memory, in the winters of 1997 into 98 and 2015 into 16, and both times the Pacific ran hot to comparable extremes. If the mechanism we've been describing is real, those two seasons should show the same signature we're watching now, a hyperactive Pacific paired with a suppressed Atlantic, and an ocean quietly loading even as the storm count stayed low. They do. And one of them produced a storm that stands as the clearest warning of what unspent ocean heat can do when a storm finally gets to use it. Take 2015 first, because it left the most vivid mark. That autumn, as a powerful El Nino peaked, the Eastern Pacific produced Hurricane Patricia. In October of 2015, Patricia underwent one of the most extreme, rapid intensification events ever observed, exploding into the most intense hurricane ever measured in the Western Hemisphere, with sustained winds around 215 miles an hour at its peak. That is not a typo, and it is not a rounding up. 215 miles an hour, a storm so strong it was near the theoretical ceiling for what Earth's atmosphere can produce. Patricia formed in exactly the environment a super El Nino builds in the Pacific, warm deep water and low shear, and it showed the world what a storm does when nothing is holding it back. It is the Pacific side proof of the same physics that has the Atlantic loaded right now. Take the brakes off warm water and a storm does not grow. It detonates. Meanwhile, on the Atlantic side of those same super El Nino years, the seasons ran quiet, just as ours is running quiet now. The strong shear suppressed development. The storm count stayed low, and to a casual observer, those Atlantic seasons looked like easy years. But quiet did not mean the ocean was cold or safe. It meant the same lid we have now was pressed down then, over water that stayed warm underneath. The suppression was real, and so was the loading. The pattern held on both sides, the Pacific overachieving and the Atlantic held down, driven by one warm patch of equatorial ocean bending the planet's circulation, exactly as it is bending it today. There is a reason forecasters lean on these analogues so heavily, and it is not nostalgia. It is that a super El Nino is one of the few situations in seasonal forecasting where the outcome is genuinely predictable, because the driver is so strong and so well understood that it overwhelms the usual noise. When the Pacific is this warm, the shear goes up over the Atlantic, the storms pile up in the Pacific, and the continental weather patterns shift in recognizable ways. It happened in 97. It happened in 2015. It is happening now. The dials are in the same positions and the machine tends to produce the same output. That is what lets a forecaster look at today's map and speak about the coming months with real confidence rather than guesswork. The winter of 1997 into 98 is the other half of the lesson, and it shows the pattern reaching well beyond the storm counts. That super El Nino drove a parade of storms along a southern track across the United States, flooding California, soaking the Gulf states, and carving a wet, stormy winter across the southern tier of the country, while the suppressed Atlantic hurricane season had already faded quietly into the background months earlier. The through line from that year to this one is not just the hurricane behaviour. It is the whole reorganisation, a Pacific loaded with storms and moisture, an Atlantic held down, and a continental weather pattern reshaped for months. When forecasters say the coming winter is likely to turn active across the south, they are reading directly off that 97 playbook and off 2015, because those are the seasons that ran this same machine to this same strength. Both analogues carry the same buried warning under their quiet Atlantic tallies. A season can post a low number and still deliver a storm that becomes the one people remember, because the ocean underneath a suppressed season is loaded, not empty. The count in the record book and the damage on the coast are two different measurements, and a super El Nino is exactly the setup where they diverge the most. History is full of seasons that looked quiet in the record and were anything but on the coast, and that is the lesson worth carrying out of these analogues. A year can finish with a below-average number of storms and still be remembered for a single catastrophic one, because the count and the damage measure two entirely different things. The count reflects how many systems formed. The damage reflects where the worst one went and how strong it got, and a loaded ocean raises the odds that the worst one gets very strong very fast. So a quiet season is not the reassurance the number implies. It is a statement about frequency, not about the ceiling. And in a super El Nino year, the ceiling is the part that should worry you. This is exactly why coastal preparedness experts dislike letting people relax during a quiet El Niño season. The public hears low activity and lets its guard down, stops watching, stops preparing, treats the season as effectively over. But the one storm that breaks through a suppressed pattern arrives to a population that has been told, all summer, that this was a calm year. The mismatch between the reassuring headline and the loaded reality is where people get caught. The value of understanding the coiled spring is precisely that it keeps you from making that mistake, from reading the low count as a promise when it is really just a description of the storms that have not formed yet. But here is where the analogues stop being reassuring and start being a warning, and it comes right back to the coiled spring. In those past events, the quiet Atlantic seasons were not entirely empty. They still produced storms, and because the ocean was loaded, the storms that did break through could be dangerous out of proportion to the season's low count. A quiet year with one bad storm is still a quiet year in the statistics, and a catastrophe on the coast where that storm lands. That is the real lesson of 97 and 2015, and the reason a low Atlantic tally this year should not be read as a promise. The pattern that suppresses the many is the same pattern that can supercharge the one, which means the story does not stay out at sea, it comes ashore, and not only as hurricanes. Because the same reorganized circulation steering all of this has already reached the middle of the United States, and it is doing things there that people are feeling right now on land far from any ocean. Part 10. The same pattern is already over your head. Everything so far has been about oceans, but the reorganized atmosphere that is dividing the Pacific from the Atlantic does not stop at the coastline. It runs straight up over the continent, and if you live in the southern United States, you have been standing underneath it for weeks. The heat that has been baking Texas, Oklahoma, and the desert Southwest, the triple-digit afternoons in Dallas, the relentless sun over Arizona, the nights that refuse to cool down, is not a separate weather story from the storms in the Pacific. It is the same story, playing out over land instead of water, driven by the same warm patch of equatorial ocean bending the same planetary circulation. Here is how the connection works. When the tropical Pacific reorganizes the way we described, it does not only change wind shear over the oceans, it also shifts the jet stream, the fast river of air that snakes across North America and steers our weather systems. Under this pattern, a dome of high pressure set up shop over the southern plains and the desert Southwest and refused to move. High pressure means sinking air, and sinking air means clear skies, no rain, and relentless compression heating as the air descends. That is the mechanism of a heat dome. It is a lid, much like the one over the Atlantic, except instead of suppressing hurricanes, it is trapping heat against the ground and cooking everything underneath it. The numbers on the ground have been brutal. Temperatures pushing into the 100s in Dallas, across Oklahoma, and throughout the desert Southwest, day after day, with essentially no relief. And relief is the key word because a heat dome does not just make afternoons hot, it kills the recovery. Normally, even in a heat wave, the temperature drops at night, giving bodies and buildings a chance to shed heat before the next day. Under a strong, persistent dome, the nights stay warm too, and the heat becomes cumulative. Occasional showers pop up and cool the atmosphere for a few hours, but they do nothing lasting. The dome reasserts itself by the next afternoon, and the bait continues. It has been, in the plainest terms, hot, and it has been hot in the stubborn, dangerous way that does not let up. Why has it parked exactly there, and exactly now? Because that is where this reorganized flow tends to build its ridge. The same shift in the tropical Pacific that suppresses the Atlantic and floods the Pacific with storms also nudges the continental jet stream into a configuration that favors high pressure over the south-central United States. It is not random that the heat landed on the southern plains rather than the northern ones. It is the continental signature of the very same driver we have been tracking across two oceans. The storms in the Pacific and the heat over Dallas are cousins, born from the same reorganization of the atmosphere, and once you see that, the weather map stops being a collection of separate events and becomes a single connected system with one source. It is worth being concrete about what this kind of heat actually does, because the anomaly numbers can go abstract fast. When a heat dome refuses to release at night, the danger compounds. The human body relies on the cool of the evening to recover, and so do buildings, livestock, and the power grid. When the overnight low in a place that should be dropping into the low 70s instead holds in the upper 80s or low 90s, Air conditioners never get a break. Demand on the grid stays pinned near its peak around the clock, and the risk of heat-related illness climbs sharply, especially for the elderly and for anyone without reliable cooling. This is why forecasters increasingly treat the nighttime temperature as the real hazard in a heatwave, more than the headline afternoon number. A hot afternoon is uncomfortable. A hot afternoon followed by a hot night, repeated for a week, is what actually hurts people. The mechanism that makes it so relentless is worth understanding, because it is the same physics of sinking air we met over the Atlantic, just turned to a different purpose. Under a dome of high pressure, air is descending through the atmosphere, and as air sinks, it is compressed by the greater pressure lower down, and compression heats it. This is not heat arriving from somewhere else. It is heat generated by the sinking itself, which is why a heat dome can keep breaking records day after day without needing any new hot air imported from outside. The dome manufactures its own heat, continuously, as long as it sits there. And because the sinking air also suppresses cloud formation, the sun beats down on the ground unobstructed, adding surface heating on top of the compression heating. Clear skies, sinking air, and no overnight relief. That is the recipe, and it has been running over the southern United States for weeks. There is a deeper symmetry here that ties it straight back to our central thread. The lid over the Atlantic and the dome over the plains are cousins, both expressions of sinking, stabilizing air organized by the same reorganized circulation. One suppresses hurricanes by drying and shearing the atmosphere over the ocean. The other traps heat by capping the atmosphere over the land. Different victims, same underlying behavior, same distant driver. When you see the heat and the storm-free Atlantic as two kinds of lids set by one hand, the map finally coheres. The Super El Nino is not causing a dozen separate problems. It is imposing one pattern, and the heat dome is simply the version of that pattern that happens to sit over people's houses. And the heat is only the most obvious of the fingerprints. The same Pacific that is exporting storms has also been exporting moisture, and that moisture has been showing up in the United States in places and in ways that are genuinely strange. To see the patterns reach, you have to follow the water, because it has been turning up where it does not belong. Part 11. The monsoon that showed up in the wrong places. Follow the moisture and the pattern gives itself away. This entire month has been full of surprises across the lower 48, and most of them trace back to one thing: an unusual amount of moisture streaming out of the Pacific and into the western United States. That moisture has amplified what is called the monsoon, the seasonal surge of humidity that normally brings afternoon thunderstorms to the desert southwest in late summer. But this year the monsoon has not stayed in its usual lane. It has been juiced, pushed harder and farther than it typically goes, and the results have been showing up well outside the areas that normally see this kind of weather. Flooding has appeared much farther north than is normal for this time of year, in places that do not usually catch the monsoon's reach. And then there is the detail that stops meteorologists in their tracks. A few weeks ago, there were tornado warnings near Salt Lake City. If you're not from that part of the country, that might not register as unusual, so let me make it clear. Tornado warnings in that area almost never happen. It was, by the reckoning of the forecasters watching it, the first time in something like 10 to 15 years that tornado warnings had been issued there. That is not a routine severe weather day. That is the atmosphere doing something it has not done in over a decade, in a place that is supposed to be too dry and too high for it, and it happened because this pattern shoved Pacific moisture into terrain that rarely receives it. There is another oceanic fingerprint on all of this, and it sits just off the coast. A warm tongue of water has set up off Baja California, an extension of the same warm Pacific signature that defines this El Nino. That warm water off the coast has helped drive record-breaking temperatures into Arizona and Southern California, feeding heat and moisture into the southwest from the ocean side while the heat dome bakes it from above. It is the same theme again, an ocean anomaly reaching onto land and rewriting the weather, the marine expression of the exact pattern producing everything else. Step back and look at what the moisture is telling you. The Pacific is not only building storms out at sea, it is exporting its excess energy and water vapor onto the North American continent, amplifying the monsoon, driving floods into unfamiliar country, and sparking severe weather in a place that had not seen a tornado warning in a decade or more. These are not disconnected oddities. They are what it looks like when a super El Nino loads the atmosphere over the western United States with more moisture than it knows what to do with. The same driver, the same warm Pacific, reaching 1,000 miles inland. To appreciate why the Salt Lake City tornado warnings are such a striking signal, you have to understand what it normally takes to make a tornado, and why that part of the country almost never assembles the ingredients. Tornadoes need three things stacked together. Instability, meaning warm, moist air near the surface with cold air aloft so that thunderstorms can tower. Moisture, real low-level humidity to fuel them. And wind shear, the change of wind with height that gives a storm its rotation. The interior west is usually too dry to supply the moisture, and too elevated to build the deep instability, which is why the region can go a decade or more without a genuine tornado threat. For warnings to fire there, something had to truck in an unusual amount of low-level moisture and pair it with the right wind profile. That something was this pattern, shoving Pacific humidity into terrain that is built to stay dry. The flooding fits the same story, and it is worse than it sounds because of where it happens. Arid and semi-arid terrain does not absorb sudden rain well. The ground is hard, vegetation is sparse, and water that falls fast runs off immediately, funneling into dry washes and canyons that can go from empty to raging in minutes. Add in the burn scars left by recent wildfire seasons, where the soil has been rendered nearly waterproof, and even a modest cloudburst can produce dangerous flash flooding far from any river. So when this pattern drives extra moisture farther north than usual, the consequence is not a gentle soaking. It is flooding in places that have neither the drainage nor the expectation for it, which is exactly what has been happening. The warm tongue of water off Baja California deserves a closer look too, because it shows the ocean and the land feeding each other. That ribbon of unusually warm water along the coast does two things. It raises the humidity of the air flowing inland, loading the atmosphere over the southwest with more moisture, and it removes the cooling influence a normal, cooler coastal ocean would provide, so the sea breeze that might otherwise take the edge off the heat instead arrives warm. The result is record temperatures pushing into Arizona and Southern California, driven partly from above by the dome and partly from the coast by that warm water. It is one more place where a piece of the El Niño-warmed Pacific reaches directly onto the continent and rewrites the local weather. And here is the part that makes the pattern feel almost deliberate, though of course it is not. While the west and the south have been drowning in heat and moisture, another part of the country has been experiencing something close to the opposite, and the boundary between the two has been sharp. The United States has been in effect cut into two different weather worlds this month, and the line between them is drawn by the same jet stream this pattern has bent into place. To understand the split over the country, you have to understand the wind that is dividing it. Part 12. A country cut in two. While the southern plains have baked, a very different story has been unfolding across the Midwest, the Ohio Valley, and the Northeast. For several weeks now, those regions have been under strong northwesterly and westerly flow, a persistent push of air coming down from the north and west. That flow has done the opposite of the heat dome. It has dragged much cooler air into the northern tier of the country, holding temperatures well below average for this time of year across the Midwest and into the Northeast, even as Texas and Oklahoma roasted. One country, two climates, separated by a few hundred miles and one bend in the jet stream. This is the jet stream acting as a fence. On the southern side of it, under the ridge of high pressure, the air sinks, the sky stays clear, and the heat builds without escape. On the northern side, the flow of cooler air keeps things suppressed and comfortable, sometimes downright cool. The exact position of that boundary determines who gets which world, and this summer the boundary has been drawn in a way that locks Texas, Oklahoma, and the desert southwest into heat, while giving the Midwest and Northeast a reprieve. That configuration, the southern ridge paired with cooler northern flow, is itself part of the El Niño influence pattern. The same reorganized circulation that decides which ocean makes storms is deciding which half of the country bakes. It is worth pausing on how unusual it feels to have this much contrast at once. In a typical late summer, the whole country tends to share a broadly similar warmth, with regional variation around the edges. This year the variation is not around the edges, it is the main feature. You can drive from a state running 30 degrees above its seasonal normal into a state running below normal in a single day. and the reason is that the atmosphere has been forced into a highly amplified pattern, with a strong ridge in one place and strong troughing in another. Amplified patterns like this, with big north-south swings in the jet stream, are exactly what tend to show up when a powerful driver like a Super El Nino is bending the flow. A sleepy, flat jet stream gives you bland, uniform weather. An amplified one gives you extremes stacked right next to each other, which is precisely what the map has been showing. The wind doing the dividing is worth picturing properly, because it is the same jet stream that governs so much of this story. The jet stream is not a straight line. It meanders in great north-south waves as it circles the planet, and where it bulges northward you get a ridge, a dome of warm high pressure, and where it dips southward you get a trough, a zone of cooler air and unsettled weather. This summer the flow is locked into a strongly amplified configuration, with a persistent ridge anchored over the south-central United States and troughing to the north and east. The southern plains sit under the ridge and bake. The Midwest and Northeast sit closer to the trough and stay cool. The sharpness of the boundary between the two is just the steepness of that jet stream wave made visible in the temperature map. What makes a pattern like this so stubborn is that these big atmospheric waves can lock into place and resist moving for weeks. When the jet stream amplifies into a deep ridge and trough couplet, the whole configuration can stall, feeding back on itself, so the ridge keeps rebuilding over the same real estate and the trough keeps digging in the same spot. Meteorologists have names for the most extreme versions of these blocked patterns, but the important idea is simple. An amplified jet stream does not just create extremes, it makes them persistent, which is why the heat has not been a passing spell, and the cool has not been a brief break. The pattern has been welded in place. There is a real cost to living on either side of that boundary. On the hot side, farmers watch crops bake through the critical late summer stretch, ranchers haul water, and utilities strain to meet round-the-clock cooling demand. On the cool side, the below-average temperatures can be a relief, but an unusually cool, wet stretch has its own consequences for growing seasons, and for anyone whose plans assumed a normal late summer. And the boundary itself, where the hot and cool air masses grind against each other along the jet, is exactly the zone where storms fire, which becomes important the moment the pattern starts to shift. The fence between the two worlds is not just a temperature line, it is a battleground. And this is not a static picture. The boundary is about to move, and when it does, the heat that has been trapped in the south is going to go on the march. That is the near-term forecast, and it matters, because it turns this pattern from something you read about into something that is going to land on tens of millions of people over the next 2 weeks. So let us walk through exactly what the atmosphere is set up to do next, because the heat is not done. It is about to spread, and then eventually it is going to break in a way that brings its own kind of danger. Part 13, the next 2 weeks. The heat builds. If you like the heat, the next stretch is built for you, and if you do not, brace yourself because the numbers coming are extreme. Heading into the final days of August, temperatures across the central part of the country are set to climb far above normal. We're talking about readings 25 to 30 degrees Fahrenheit above average across Nebraska, Kansas, and back into Iowa as the weekend arrives. To be clear about what that anomaly means, it is the difference from the seasonal normal, so a place that would ordinarily sit in the middle 80s could be pushing well past 110. That is a massive departure, the kind that stresses power grids, crops and people all at once, and it builds from there. By the beginning of the following week, the core of the heat is projected to intensify and spread into a broad zone running from Oklahoma City all the way up into Minneapolis and Wisconsin, with temperature anomalies reaching as much as 30 to 35 degrees above average. Think about that footprint. This is not a local hot spell. It is a slab of extreme heat draped across the middle of the country, from the southern plains into the upper Midwest, all of it running dozens of degrees hotter than the calendar says it should. The last 2 days of August in particular look like a genuine bake across the Great Plains. There is a modest break in the choreography. Around Tuesday or Wednesday of that stretch, a cold front is expected to push through and knock temperatures down at least somewhat across the northern plains. But, and this is the important qualifier, the relief is partial and it is northern. The heat is forecast to hold its grip across much of the Midwest and the central plains even after the front passes. Places like Kansas City and St. Louis are looking at readings around 25 to 30 degrees above average as the calendar turns into early September. The front reshuffles the northern edge of the heat, but it does not end it. The dome simply repositions, and the core of the warmth slides east and holds. Now connect this back to the driver, because it is easy to lose the thread in a pile of temperature numbers. This heat is not a random late summer wave. It is the continental expression of the amplified, El Nino-influenced pattern we have been tracking all along. The same reorganized jet stream that fenced the country into two climates is now going to let the southern ridge expand and shove its heat north and east, which is why the extreme anomalies are set to bloom across the plains and Midwest. The storms in the Pacific, the silence in the Atlantic, and this slab of heat over America are three faces of one pattern. When you see 35 degrees above average from Oklahoma to Minnesota, you're looking at the same machine that has the Pacific overflowing and the Atlantic locked shut. To feel the scale of a 30 to 35 degree Fahrenheit departure from normal translated out of the abstract. In late August, a normal afternoon across parts of the Central Plains might top out somewhere in the middle to upper 80s. Add 35 degrees to that, and you're talking about readings well into the 100 and teens in spots, in a region where the humidity can push the heat index, what it actually feels like on your skin, even higher. That is not a hot summer day. That is a public health emergency spread across multiple states at once, and it lands on a part of the country where a lot of people work outdoors, where agriculture runs on human and animal labour in the fields, and where the electrical grid was not necessarily built for a week of everyone running their air conditioning at maximum through the night. The role of the overnight low comes back here with force. When the air itself is running dozens of degrees above normal, the nights do not recover, and the heat becomes a continuous load rather than a daily cycle. Records set during events like this are increasingly set in the overnight minimum temperatures, the warmest nights ever recorded for a date, rather than in the afternoon maximums. It is a quieter kind of record and a more dangerous one because it is the failure of the night to cool that turns a heat wave from an inconvenience into a killer. Across the plains and the Midwest over the next couple of weeks, those overnight records are the ones to watch. The cold front that arrives midweek is a useful illustration of how these patterns actually shift, rather than simply switching off. A front does not so much defeat the heat as rearrange it. It sweeps through the northern plains, knocks temperatures down there for a day or two, and reminds everyone that fall is coming. But the ridge does not collapse. It repositions, sliding its core east and holding the heat in over the Midwest and Central Plains, which is why Kansas City and St. Louis stay baked into early September, even after the northern plains catch a break. The heat is not gone. It has moved, and it is the same heat, driven by the same ridge, organized by the same pattern. Watching where it goes tells you where the boundary and the next round of storms will set up. But no heat dome lasts forever, and the way this one is likely to break is its own story, because the collision between built-up heat and the first strong storm systems of the season is exactly the recipe for the severe weather that tends to close out a pattern like this. The heat is the setup. The break is the payoff, and it is not a gentle one. As we move into September, the atmosphere is going to try to tear this pattern down, and that process is going to put a lot of people under the threat of storms. Part 14. When the dome breaks. A heat dome is a temporary tyrant. It rules absolutely while it lasts, but it always falls, and the way it falls is rarely gentle. When you build up this much heat over the middle of a continent, and then a strong storm system finally arrives to challenge it, the collision between the trapped hot air and the incoming cooler air is exactly the environment that breeds severe weather. The heat is the fuel. The arriving system is the trigger. Put them together and you get the thunderstorms, the wind, the hail, and sometimes the tornadoes that tend to mark the end of a pattern like this. So even as the heat builds over the next 2 weeks, the seeds of its violent breakdown are already visible in the forecast. Look at what is already on the map in the short term. There is a large storm system moving across the East Coast, bringing some isolated severe weather, and out in the plains there is a chance for a couple of severe storms across Nebraska and South Dakota. As the weekend arrives, a new storm system is set to organize across the northern plains, and this one bears watching, because it could fire supercells over the Dakotas. Supercells are the rotating thunderstorms that produce the most dangerous weather, and their presence raises the possibility of an elevated tornado threat. The confidence on that is not high yet. There is real uncertainty in exactly how it comes together, but the ingredients are lining up in a way that puts the northern plains on notice for the weekend. The activity does not stop there. Heading into Sunday and Monday, storm systems are expected to continue across the Great Lakes, the upper Midwest, and into the Northeast. It is a busy stretch, though not a catastrophic one, more a series of rounds than a single historic outbreak. After that, the pattern quiets for a bit, with no major systems clearly on the horizon for a few days. But the models are hinting at something larger taking shape as the calendar moves deeper into September, and this is where the forecast gets genuinely interesting. The main American forecast model has been suggesting that much larger storm systems could become reality over the first 10 to 15 days of September. If that verifies, it would mean a more elevated risk of severe weather across parts of the country, as those bigger systems tap into the heat and moisture that this pattern has stockpiled, and there is an even more dramatic possibility tucked into the model output. As the pattern amplifies and colder air starts to plunge down behind these systems, there is a chance of the first snow of the season across the Rockies, potentially the first meaningful snowfall there in quite a while. Heat this week, and the possibility of snow in the high country within a couple of weeks. That whiplash, from record warmth to an early shot of cold, is itself a signature of a highly amplified pattern, the kind a strong driver like this one tends to produce. It helps to understand why the edge of a heat dome is such fertile ground for violent weather, because it is not a coincidence that the storms fire right where the heat has been. Around the northern and western flank of a strong ridge, forecasters sometimes talk about a ring of storms, because that is where the hot, unstable air under the dome meets the jet stream and the disturbances riding along it. The heat has spent weeks loading the atmosphere with energy, what meteorologists measure as instability. The fuel a thunderstorm converts into towering updrafts. All that stored fuel needs is a trigger and some wind shear to organize it, and the arriving storm systems supply exactly that. So the very heat that felt so oppressive becomes the ammunition for the storms that end it. The Dakota setup for the weekend is a textbook version of this. You have hot, unstable air pumped north ahead of an approaching system, a boundary where that air is forced to rise, and enough change of wind with height to make the resulting thunderstorms rotate. Rotating thunderstorms are supercells, the most dangerous kind, capable of very large hail, destructive straight-line winds, and tornadoes. The reason the tornado threat carries real uncertainty is that it hinges on the fine details, how much low-level moisture actually arrives, how the winds turn with height in the lowest few thousand feet, whether the storms stay discrete or clumped together. Those are the hardest things to nail down days in advance, which is why the forecast can confidently flag the risk while honestly refusing to promise exactly how it plays out. The possibility of early snow in the Rockies within the same 2-week window is the whiplash that reveals how amplified this pattern is. To get record heat and then mountain snow in such quick succession, you need the jet stream to swing violently, first bulging far north to build the heat, then plunging far south to drag cold air down behind the storm systems. That kind of big, fast swing is the signature of a strongly forced pattern, the fingerprint of a powerful driver bending the flow into deep waves. It is the same amplification that split the country in two, now expressed in time instead of space, warmth and cold trading places over a matter of days. When you see that kind of whiplash in a forecast, it is a tell that the atmosphere is being pushed hard, which is exactly what a Super El Nino does. The honest caveat is that all of this is more than 10 days out, and at that range the details will change. But the broad direction is consistent, and it connects to the through line of this whole story. The heat dome is going to break down as we head toward fall, and when it does, the jet stream will lift and reload, bringing severe weather and a more active pattern back into the picture. That transition is not the end of the El Nino pattern. It is the pattern evolving into its next phase, the phase that carries us into fall and winter. And the winter this pattern is setting up is the biggest legacy of all, because a Super El Nino does not just rearrange a hurricane season, it rewrites an entire cold season, and the one it is writing right now is aimed squarely at the southern United States. Part 15. The Winter Being. Written right now. The most consequential thing about this Super El Nino may not be anything happening this week. It may be the winter it is quietly assembling for the months ahead. Because if there is one thing a strong El Nino reliably does, it is reshape the storm track for the cold season, and the reshaping favours a very specific and very active outcome for the southern half of the country. The forecasters watching this pattern are already saying it plainly. As we head into fall and winter, the storm track is expected to shift dramatically to the south, And that shift should light up the southern tier of the United States with storm after storm. Here is why El Nino does this. During the winter, the warm tropical Pacific energizes the southern branch of the jet stream, the subtropical jet, giving it more moisture and more punch than it normally carries. That invigorated southern jet becomes a highway for storm systems, steering them across the southern United States rather than letting them ride farther north. The result in a strong El Nino winter is a parade of storms tracking across the south, from the desert southwest through Texas and the Gulf states, across what is sometimes called Dixie Alley, and up the East Coast. It is the same mechanism that flooded California and soaked the South in the big El Nino winters of the past, and it is being set up again now. What that means on the ground is an active and at times stormy winter for the southern plains, the Gulf states, Dixie Alley, and the East Coast. Several big storm systems more than a quiet winter would bring tracking along that southern route. It does not mean the northern part of the country escapes winter, of course. There will still be winter storms across the Midwest and the Northeast because cold air and moisture will still collide up there. But the tilt of the pattern, the favoured zone for the biggest and most frequent action, shifts south in a way that is characteristic of exactly this kind of strong El Nino. The South, which often sits on the sidelines of the winter storm season, moves to centre stage. The way that moisture arrives on the West Coast in these winters is worth a mention, because it is one of the more dramatic expressions of the pattern. When the energized subtropical jet taps a long plume of tropical moisture and aims it at the coast, the result is what forecasters call an atmospheric river, a narrow corridor of the sky carrying an enormous flux of water vapour, sometimes reaching back toward the tropics in a feature nicknamed the Pineapple Express. These systems can unload staggering amounts of rain and mountain snow in a matter of days. In past strong El Nino winters, they have both rescued the West from drought and, in the same stroke, driven flooding, mudslides, and record snowpack. It is the classic El Nino duality, too much and too little arriving as the same event, and it is the kind of winter this pattern favours. Across the south and southeast, the active storm track carries a different signature, one that includes severe weather even in the cold season. The same parade of systems that brings rain to the Gulf can, when the ingredients align, produce winter and early spring severe thunderstorm and tornado episodes across the southeast, a region that sees some of its worst outbreaks in exactly these El Nino-influenced patterns. So the southern shift of the storm track is not only a matter of more rain and mountain snow, it can mean a more dangerous convective season for parts of the south as well, another way the same driver reaches into a different season and a different hazard. And notice how seamlessly this connects to everything we have discussed. The same super El Nino that has the Pacific overflowing with cyclones and the Atlantic locked shut is the driver that will energize the southern jet and reroute the winter storm track. The quiet Atlantic hurricane season and the active southern winter are not two separate forecasts. They are two chapters of the same story. The near-term chapter and the cold season chapter, both written by the same warm patch of equatorial Pacific water. When you understand the driver, you can see months into the future with more confidence than usual because the driver is strong enough to dominate the outcome. That is the strange gift of a super El Nino. It makes the planet's weather, for a while, more predictable, even as it makes it more extreme. The physics of why El Nino reroutes the winter is worth making concrete, because it is the same coupling of ocean and jet stream we have relied on all along. In winter, the temperature contrast between the warm tropics and the cold pole sharpens, and the jet streams strengthen. A strong El Nino, by keeping the central and eastern tropical Pacific unusually warm, energizes the southern branch of the jet in particular, the subtropical jet, loading it with moisture and speed. That invigorated southern jet becomes a conveyor belt for storm after storm, and it tends to run across the southern United States, which is why El Nino winters so reliably light up the south. The same warm water that suppressed the Atlantic in summer becomes, in winter, the engine that drives storms across Texas, the Gulf, and the southeast. The last comparable events show what that looks like on the ground. In strong El Nino winters, California and the southwest have seen repeated storms and heavy precipitation, drought-busting in some years and flood-producing in others. The Gulf states and the southeast have seen active, wet, stormy stretches. Even the southern mountains can pick up significant snow when the moisture from that southern jet runs into cold air. It is a genuinely different winter from the quiet, dry, cold season the South often gets, and it is one of the most dependable consequences of a strong El Nino, which is why forecasters are comfortable pointing to it months ahead. The driver is strong enough that the winter outcome is already coming into focus. None of this means the northern half of the country sits it out. Cold air will still spill south, and where it collides with the moisture riding that active southern storm track, the Midwest and Northeast will still get their winter storms, potentially significant ones. The point is not that the North goes quiet. It is that the centre of gravity of the winter, the favoured zone for frequent moisture-rich storm systems, shifts south in a way it does not in a normal year. The South moves from the sidelines to the main stage, and that shift is written directly into the pattern we are watching set up right now, in late August, months before the first winter storm arrives. There is one more chapter that most people are not thinking about though, and it is the one that ties the whole thing back to where we started, to the loaded Atlantic and the coiled spring. Because the peak of El Nino and the tail end of hurricane season overlap, and that overlap is where the danger we described earlier is most alive. The story of the quiet Atlantic does not close when summer ends. If anything, the fall is when it matters most. Part 16. The fall is when the spring is most loaded. Hurricane season does not end in August. It runs through the fall with a climatological peak in the first half of September and significant activity often continuing into October and even November. And here is the uncomfortable overlap. A super El Nino typically strengthens toward its own peak in the late fall and early winter, so through the heart of the remaining hurricane season, the Atlantic will be sitting under the influence of an El Nino that is at or near its most powerful, which means the shear that has suppressed the basin all summer is likely to remain in place. On the surface, that sounds like continued good news, more suppression, fewer storms. But run it through everything we have learned and it reads differently. It means the Atlantic will keep loading. It means the reservoir of unspent heat keeps deepening through the exact weeks when historically the biggest storms of the season form. This is the coiled spring extended into the fall, and it is why the story that started with a quiet map does not resolve into a quiet season. The longer the lid stays clamped, the more energy accumulates beneath it, and the higher the stakes of any single window where the shear happens to relax. Late-season storms have a way of being memorable, precisely because they form over water that has had all summer to warm. In a year like this one, that water has also had all summer to go unspent. So the fall carries a particular kind of risk, not of many storms, but of the one storm that finds a gap in the shear and detonates over a fully charged ocean. The calendar is part of why the fall is so loaded. Atlantic hurricane activity does not spread evenly across the season. It climbs through August and peaks, on average around the middle of September, then tapers through October and into November. So the weeks just ahead are, historically, the very heart of the season, the stretch when the largest and most numerous storms have always been most likely. In a normal year, that peak is when the Atlantic is at its most dangerous. In this year, that peak arrives with the basin having spent the entire lead-up quietly stockpiling heat instead of spending it. The most active part of the calendar is about to overlap with the most loaded the ocean has been. That overlap is the crux of the coiled spring idea extended into the fall. A suppressed season does not lower the ceiling on what a single storm can do. It raises it by leaving the fuel untouched, and it stacks the highest ceiling of the year on top of the weeks when storms are most likely to try. Each week the lid holds, the reservoir deepens, and the potential intensity of any storm that does break through climbs. The suppression and the danger grow together, which is the opposite of how our instincts read a quiet season. We hear low storm count and think the threat is receding. In a super El Nino year, the threat per storm is doing the opposite of receding, even as the count stays low. And it is not only the deep tropics that matter in the fall. Some of the most dangerous late-season storms form closer to home, in the Western Caribbean and the Gulf, where the water is warmest and where a system can go from nothing to a major hurricane in a day or two, if the environment briefly allows it. Those are the setups that keep forecasters up at night in an El Nino year, because the suppression lulls everyone into treating the season as over, while the ocean quietly stays primed. The disturbance we talked about earlier, the one that might become Dolly, is an early low-stakes version of that scenario. The higher-stakes versions come later, when the water is even warmer, and the season is at its climatological peak. The fall also changes where the danger tends to come from, and that shift is part of why complacency is so risky. Early in the season, the classic threat is the long-track storm rolling off Africa and crossing the open Atlantic. By October and into November, the action moves closer to home, into the Western Caribbean and the Gulf of Mexico, where the water stays warm the longest and where homegrown systems can spin up with little warning and a short distance to land. These late-season, close-to-shore developments are among the hardest to prepare for, because there is often no long lead time as a storm crosses an ocean, just a system forming almost on the doorstep and intensifying over water that this year has been quietly charging all summer. A basin that everyone has written off as finished is exactly the setup those storms exploit. So the pattern does not let go. It carries straight through from the storms spinning in the Pacific right now, to the heat over the plains, to the severe weather that will break the heat, to the active southern winter, and running underneath all of it, the loaded Atlantic waiting to see whether the lid holds through the fall. One driver, one warm patch of ocean, threading through every season and every region, producing opposite extremes that are all, secretly, the same thing. That is the terrifying pattern in our title, fully drawn. Not the 6 or 7 storms in the Pacific by themselves, and not the empty Atlantic by itself, but the recognition that they are one system, and that the quiet half is the half that is being wound up. Which leaves us with the question this all points toward, the one that cannot be answered yet, only watched. We have traced the driver, the mechanism, and the stakes. We know why the Pacific cannot stop and the Atlantic cannot start. We know the quiet is loading, not resting. What we do not know, what nobody can know until it happens, is whether the lid holds. And that uncertainty is not a gap in the story. It is the point of it. Part 17. What the silence is really telling us. Step all the way back and look at what we have actually been describing, because it is stranger and more unified than any single piece of it suggests. On one planet, at one moment, one ocean is producing more storms than it can name, and the ocean beside it is producing almost none. A continent is split down the middle, one half baking under record heat and the other running cool, with floods and out-of-season tornadoes showing up in between. A winter is being drafted months in advance, aimed at the southern states, and underneath a quiet, reassuring stretch of the Atlantic, a reservoir of heat is deepening week by week. Every one of those things is the same thing. All of it traces back to a patch of the Pacific along the equator running nearly 5 degrees Fahrenheit above normal, bending the circulation of the entire atmosphere to its will. That is the part worth sitting with. We tend to experience weather as a series of separate events, a storm here, a heat wave there, a quiet hurricane season, as its own piece of good luck. But a super El Nino reveals the machinery underneath, the connectedness that is always there and usually hidden. Pull one lever in the middle of the Pacific and storms bloom in one ocean, die in another, heat piles up over Texas, moisture floods into Utah, and the winter storm track slides south. It is a humbling thing to see laid out, because it means the weather over your own head this week is tied, through a chain of cause and effect thousands of miles long, to the temperature of a distant sea. There is something almost humbling in watching a driver this large operate, because El Nino is not new, and it is not ours. The Pacific has run this oscillation for as far back as the climate record reaches, warming and cooling on its own rhythm across the centuries, long before anyone was measuring an index or naming a storm. What is new is only our ability to see it whole, to watch in near real time as one warm patch of ocean bends the weather of an entire hemisphere. We did not build this machine, and we cannot switch it off. We can only read it, and the reading this year says the Pacific is running one of its strongest performances in the modern record, and it reframes what silence means. We are trained to hear a quiet forecast as safety. No storms, no threat, nothing to worry about. But this year the silence over the Atlantic is not the sound of safety. It is the sound of something being held back. The same force keeping that ocean quiet is the force loading it, and the calm is not the absence of danger but the storage of it. A dead quiet Atlantic in the middle of a historic El Nino is not a season with nothing in it. It is a season holding its breath. That is the uncomfortable truth the pattern is trying to tell us if we are willing to read the quiet correctly. None of this is a prediction of doom. It may well be that the lid holds all the way through, that the shear never relaxes at the wrong moment, that the loaded ocean is never given a storm to spend itself on, and the season ends with a low count and no catastrophe. That is a real and even likely outcome. The point is not that disaster is certain. The point is that the quiet is not the same as safety, and understanding the difference is what lets you watch this season with clear eyes instead of false comfort. The pattern is legible. The driver is known. The stakes are set. What remains is the one thing no forecast can settle in advance. There is a discipline in reading a pattern this way, and it is worth naming, because it is the difference between fear and understanding. Nothing in this story is a prediction that catastrophe is coming. The honest forecast is that the Atlantic will probably stay quiet, that most disturbances will keep losing to the Shear, that the loaded ocean may never be handed a storm to spend itself on, and that the season could end with a low count and no disaster at all. That is a real and maybe even the most likely outcome. The value of understanding the pattern is not that it lets you predict doom, it is that it lets you hold two true things at once, that the season is quiet, and that the quiet is not the same as safe. That is the whole reframing this pattern offers, if you are willing to take it. A super El Nino pulls back the curtain on how connected the planet's weather really is, how one warm patch of ocean can spin up storms in one basin, silence another, bake a continent and script a winter, all at once, all from a single lever. And it teaches you to distrust the easy reading of a calm map, to ask not just whether something is happening, but whether something is being held back. The storms in the Pacific are loud and obvious. The danger in the Atlantic is silent and stored. Learning to take the silent one as seriously as the loud one is the entire point. So here is where we actually stand, and here is the question to carry with you. Out east of the islands, a single smudge of clouds is trying to decide whether to become a storm over an ocean that has spent an entire summer quietly filling with unspent heat, while a super El Nino holds the lid down tight. Most of these disturbances lose. This one probably will too. But the ocean underneath keeps getting more loaded with every week the Atlantic stays silent, and the shear that is holding everything back is the one ingredient that can vanish in a matter of days. So the real question is not whether the Pacific will keep making storms. It will. The real question is the one hanging over the quiet ocean, the one we will only be able to answer by watching. If the lid ever lifts, even once, over that warm and waiting water is a silent Atlantic. Really the good news we have been telling ourselves it is, or is it the setup for the single storm that outruns every forecast we made?